Hello, good evening everyone. Today we will discuss about the assignment number 4. Here we will discuss about the interstitial and substitutional site and in the HCP and FCC one, and also we will discuss about the coordination number and the relation between the octahedral radius and the tetrahedral radius. We will cover this assignment tutorial one today. Okay, so let's start with the question number 1. So now in question number 1, which type of the interstitial site will the ion Fe2 positive and Fe4 positive occupy in the iron titanate? That is FeTiO3 occurs in the eliminant crystal structure that consists of an HCP arrangement of the ions. So we have to tell where my Fe2 positive and the titanium 4 positive occupy in the iron titanate. Iron titanate is basically my having the structure of AbO3. O is oxygen here, A and B are my Fe and the titanium. Okay, if I go, you can see from here, this is the crystal structure of the FeTiO3, and here you can see that your this atom, this is your Fe1, Fe iron 1 is connected to the oxygen. O is your oxygen, and the here this titanium is also connected to the oxygen. Generally in this, oxygen will occupy at the corner of the cell, corner of the cube 1. So if I say this my Fe, if I'm this Fe make a structure of Fe will be coordinated with the 6 oxygen, or we can say this is the bond of Fe oxygen 1, or this is the equivalent axial and the equatorial one. They have described this one. Similarly for the titanium one, that is also existing in the form of the TiO6. Okay, so now if you rotate the structure, because here we have to find out the coordination where my what kind of the interstitial site, I mean where my Fe2 positive and the this Ti positive will sit in the this FeTiO3 ion. So how where they are sitting, I mean which kind of the position they are occupying, whether it is the octahedral one or the tetrahedral one. So we have to see from the crystal structure. If I see from here, you can see this Fe and the titanium both are bounded with the your oxygen anions. Yeah? If I rotate this same crystal one with this one, and you can find out this Fe is connected to the how many oxygen one way? I mean what kind of the position is there? This is because these oxygen are in one plane, and the two oxygen these are oxygen in the one plane. This oxygen and this oxygen are the outer flame. Basically what we have in the tetrahedral one, we have this structure. This is the my tetrahedral one. If I talk about the octahedral is having, this is here the my atom is sitting it here somewhere here in the between of this octahedral position. And so in octahedral one, this one, just a second. So in the octahedral one, this is the my 4 atom are which are in the my plane one, that is, and the 2 atom that are connected with these 4 atoms, and one is lying at the above and another is lying below one. in this alloy or the solid one solution, there is, it is not necessary it should be the regular one, both the tetragonal or the orthogonal. It will be the distorted or will be the rotated one. Okay, so here we have to find out which kind of the crystal they are site they are occupying, whether it is the octahedral or it is the tetrahedral one. If I see from here, see from this atom is connected to the 6-ozone or having the structure of like this one. So I can say this, my Fe atom is occupying, Fe2 positive one is occupying the octahedral position, octa, octahedral site. Okay, and if I talk about the titanium 4 positive, this is the titanium. Blue one is representing by the titanium, or oxygen is represented by the red one, and the Fe is represented with the gold one. So if I look at the this titanium 4 positive one, this is also forming the octahedron one. So here you can see this is one, this is connected this one, and this one. There is above and below one. Or here you can say this one is disconnected to here, this is one is behind one is this one, and both are these are two. So this is also connected with the 6 oxygen atom, both your Fe2 positive and the titanium 4 positive, both are connected with the 6 oxygen atom. So they will occupy your octahedral position one. So according to this one, for the FeTiO3, your Fe2 positive occupy the octahedral one, and the titanium 4 positive also occupy the octahedral one. So your A will be the right answer for this one. Okay. So move to the next question. Question number 2. So in the question number 2, if someone has any doubt, please write in the chat box or either unmute yourself and ask. You can ask in the discussion. We will discuss that one also. So in question number 2, it is asked what will be the stacking sequence of the zinc plate crystal structure that may be generated from the closed packed plane of the ion. Basically, what is your zinc plate? Zinc plate is your zinc sulfide. Basically, your zinc sulfide is existing in the two form. One is the zinc plate and one is the versatile something one. Okay, so this is the, so you, it is asked in the what will be the staking sequence of the your zinc plate crystal structure that will be generated from the. First, we have to know about the what is the crystal structure of your zinc plate one. Okay, so this is the crystal structure one of the zinc plate one, where this blue atom, that is blue atom, is representing your zinc 2 positive, and green one is representing your sulfide ion. So from here you can see that this your sulfide ion are basically occupying at the FCC lattice, or you can see from this, for this one this is at the center, for this one this is at the center, for this pair it is also, it is the center, and for this one, for the front one it is, and for the behind one it is. So you can see here this S2 negative, it is an ion is occupying the your FCC lattice. And what about the your zinc 2 positive? Zinc 2 positive is basically occupying your half of the tetrahedral position. That is your 4 out of the out of the 8 octant of your cube. So usually we have the uh, usually we have the uh, 8 number of the tetrahedral in your cube one, FCC one. So if I see from here, what will be the staking sequence for this zinc plate one? It will be the FCC one, because this is occupying the FCC lattice one. So this is your A will be the right answer. Okay, and you can see from here also your zinc plate and your the diamond or the cubic yes silicon carbide all having the same structure, and they are having where your this atom are at the core at the FCC lattice, but having the different motifs. In for the FCC they are having zinc Zn2 positive occupying the tetrahedral hello Pani, hello Ankit Kumar. Okay, so we are discussing the only the question number two. We just started. If you have any question, if you have any doubt, please write in the chat box or in the you can unmute yourself and you can ask in the in between also. Okay, so this if okay, I'm repeating again the question number two where it is asked we have to find out the staking sequence of the zinc plates crystal structure that may be generated from the closely packed plane of the anion. You can see from the this structure, this is the zinc sulfide one, and it is having your sulfide ion occupying the FCC lattice one, and Zn2 positive are occupying half of the tetragon, that is the 4 out of the 8 one. Okay, so this is having the crystal structure same like the diamond one and the silicon carbide one. So for this one, the FCC stacking sequence will be followed for the zinc blade crystal structure. Okay. Okay, let's move to the question number 3. In the question number 3, it is asked what is the coordination number for the cation filling the tetrahedral, octahedral position. Sorry. So in question number 3, it is asked what is the coordination number for the cation filling the tetrahedral and the octahedral position in the closed packed structure respectively. So what will be the coordination number for the cation one? If it is it is the octahedral one and it is the tetrahedral one. So you know in the tetrahedral position will be the this one where atom are sitting at the I mean at the corner of the tetrahedron one, and the in the octahedral it is having the this kind of where also the atom are sitting at the corner and the at the four atom are sitting at the plane, and the one atom is above the plane and one atom is below the plane. So you have to connect if the cation is filling the octahedral. This is the tetragon. Now your atom is sitting here. So, sorry for the inconvenience. So in the tetrahedron, your atom will be sitting here. In the octahedron, it will be somewhere here. So you have to find out the what will be the coordination number for the cation that is filling your octahedral and the tetrahedral. So if I see from here, so what will be the coordination number for the tetrahedral? This is your atom. It is say. So what will be the coordination number for this atom? Can anyone tell me what will be the coordination number for this atom sitting at the tetrahedral position 1? It is connected to the 4 atom. Yeah, this one, and this one. So the coordination number for this will be the 4 one. And if I look into the octahedral, the atom sitting at the octahedral position, so this atom is connected to the how many number of atom? It is connected to the 6 one. 4 here, that is are in the plane one. I'm talking about the regular one. In the lattice one, they are kind of the distorted one. I mean, these are not the may or may not be the regular one. One is above the one is below the one. So the coordination number for the octahedral, the atom sitting at the will be the 6. Same thing it is shown here. The if you say if I'm see the this one, if this kind of the atom, we have a one layer of atom, that is I'm defining with the green one. So this is one layer, one atom. This is the one layer. Okay, here, and now the again the second layer that is above this one, plain one. This one B atom. If I'm saying that this is my B atom. So whatever the space that is here, in between here, this is the octahedral position one. And if you look at this octahedral is connected, it is the in between the two stack of the layer. So it is will be connected with the 3 with the green one. That is, if I'm saying this is the A type, and the 3 one the red one. This is of the B type. So basically, the coordination number for the octahedral one will be the 6 one. For the same thing, if I see from the for the octahedral one, you can see here this one. If I'm talking about the these three atom only. Now we are considering it is not necessary in a crystal structure there will be the only one type of the this vacancy site, either the octahedral or the tetrahedral. It can be octahedral, it can be tetrahedral, it can exist the both kind of vacancy also. Okay, so here same thing is here when the atom is here sitting here, so it will be connected to the 6 atom here, and if atom is seated here, so it is connected to the 4 atom. I mean, the atom will be not be at the, this is the atom side, this will be the in between this here, I mean something below this point, there will be the space here, there will be, it will be sitting here. So for the tetrahedron, it will be the 4 one. So the right answer for this one will be the 4 and the 6. Okay, third A part. So what will be the, okay, let's move to the next question. In question number 4, now you have to tell me how many. Okay, in this question, please tell me. Okay, if this is a closely packed, the how many the tetrahedral word existing in the closely packed structure, and the how many will be the octahedral one. Octahedral. Tetrahedral will be the basically the 4 4 per unit cell, and your octahedral that is will be the this is any for the tetrahedral it will be the 8 per unit cell, for the octahedral it will be the 4 per unit cell. Basically the tetrahedral that is existing with the diagonal one, body diagonal, so we have on one body diagonal it is 2 number, total number of the body diagonal will be the 4, so total number of the octahedral position will be the 8 one. For the octahedral we have the we have the different scenario. So it will be the 4 per the unit cell. This is all lying on the body diagonal one, the tetragonal one. Okay. Now let's move to the next question. That is the question number 4. In question number 4, you have to tell me how many tetrahedral voids per atom will be possible in the HCP. So how many per atom? As I already told you, number of the tetrahedral voids for the FCC and for the HCP, both are having the same number of the void per atom because they are having the same closing packing fraction, but they having the different position only, but the number is the same one. For the tetrahedral, I'm just repeating it, tetrahedral one will be the 8 per 8 per unit cell. Okay, this is for the FCC one, and for the this one for the octahedral, it will be the 4 per unit cell. For the HCP one, that also professor had told you, they be the two number of the tetrahedral voids that are existing in this one. For the HCP one, total number of the tetrahedral will be the, this is, sorry, this is for the per unit. If I'm because same thing is for the HCP one. If I'm talking about the here, it is asked about the per atom. Because if we know about the FCC one, we can calculate for the HCP one also. For FCC one, what will be the number of the tetrahedral voids per atom? Basically, in the FCC, we have the 4 atom, so the 2 per atom, or octahedral will be the 1 per atom. Okay, so same thing is happening for the HCP one. So total number of the tetrahedral per atom will be the 2, and number of the octahedral will be the octahedral per atom will be the 1. Okay, so here it is asked about the tetrahedral voids. So tetrahedral voids per atom. So per atom will be the 2 1. If it is asked about the per unit cell, so it will be the 8 per unit cell, and this will be the octahedral will be the 4 per unit cell. Okay, do you have any doubt till question number 4? Please respond. If you have any doubt, please let me know. Okay, I'm assuming there is no doubt. So let's move to the question number uh, fifth one. Now is question number 5. It is asked, but which of the following statement is incorrect? You have to tell me which of the following are. First one is the substitutional solid solution is the one in which atom of the solid atom occupy the same location that the solvent atom metal atoms are expected to the occupy. And the interstitial B part is the an interstitial solid solution is the one in which the solute atoms occupy the interstices between the solvent atom. Third one is the an intermediate compound is a compound formed between the metal and the metalloids one. Fourth one is the Ni3El is a intermetallic compound. Just read this one and find out which is the correct one. So tell me the which one is the incorrect one? Is it the A? Is it the B, C, or D? So which one is the incorrect statement? Basically, the we have it is what we have in the substitutional one. As the professor has already taught you. Okay, I also asked or queried to the professor that about the pointer size, and he has mentioned that these are the recording videos. He can't change the pointer size now, so you have to be careful while watching the video and then where it is moving or he is pointing out because he can't do now it one. Okay, so let's come to the question one. So in the what is the substitutional solid solution and what is the interstitial solid solution one? What is so substitutional is basically we have lattice or motif one. Okay, we have the lattice and the motif one. One of atom is either one of the atom that is impurity or that is the atom that is occupy the already the motif site one. Interstitial is basically that it is occupying in between them. That is not occupying at the motif or the lattice one, but is occupying at the in between of them. So that is the my interstitial solid one. Intermediate compound. Intermediate is whenever any kind of the reaction or whatever it is happening. Suppose your A is going to B1, but here A converting to B, but there is something, there is any compound that is forming at in between of the stage one. Let's say because if we add some, if we add, we have already discussed in the steel formation also when we add the carbon percentage to the steel one. So when we are adding the percentage of the carbon one, so different percentage one. So in between whatever the phase that is forming, that is your the interstitial compound one. And intermetallic compound. So next one is the intermetallic compound. So intermetallic compound are basically the your sorry intermetallic compound are your basically the well defined crystal structure or the ordered one or having the well defined your stoichiometric coefficient. Well defined and they are because they are the well defined, so this will be the for this will be used for the higher temperature purpose. So now we have discussed all about the solid solution and this part. So now you have to tell me which statement is the incorrect one. Either A, B, or C or D. I mean, which of them? I mean, it's not necessarily more or two or three. One is incorrect one. So tell me the which one is the incorrect one. Is it A, B, C, or D? So tell me the which one is the incorrect one. A, B, C, or D. So in the first one, see, in the first one, it is it is said that the substitutional solid solution is the one in which atom of the solute atom that is we are mixing one occupy the some occupy the some location that solvent metal and expected to occupy. Yeah, it is true because it is the one it will occupy one of the occupancy of the already solvent atom one. So the substitutional will be the same the atom that the solute atom or the impurity occupied that is expected to the solvent atom used to occupy. Okay, so A is the correct one. Let's move to the B. So B in the interstitial, an interstitial solid solution is the one in which the solute atom occupy the interstices between the solvent atom. Yeah, it is also 2 because the whatever the solute atom, the solute atom will occupy the interstices between the solenoid, and this occupancy depend upon the size of the material where it is. I mean, whether it occupy the interstitial one or the substitutional one, it depend upon the size of the solute atom. Okay, so B is also the correct one. So now move to the C1. So C is the an intermediate compound, is the compound formed between the metal and the metalloids. Intermediate is a compound the form between metal and metal. It can be between metal and the metal, but it is not necessary between. It is formed between the metal and the metalloid. It is not a general statement. It is a particular statement. So this is not the correct one. And the fourth one is the Ni3 aluminum is an intermetallic compound. Yeah, this is because here it is the your nickel is 75% occupied and aluminum is your 25% occupied. So they are having the well-defined stoichiometry. So this is the intermetallic compound. So D is the also the correct one. So the according to your question number, so C is the right answer because in intermediate compound is the compound formed between the metal and the metal. It can be between either metal or metal. So C will be the right answer for this question number 5-1. Okay, now move to the question number 6 and read this question. So in the question number, we have to tell me which is not a homerotary condition. What are the homerotary condition? As the professor also told you in the class, but I am also telling you. So which are the homerotary condition one? So one is that the crystal, the size of atom, the size difference between the two elements should not be greater than the 15%. It should be less than the 15%. First one is this one. Second one, the electronegativity of the both the atom, the difference in your electronegativity in the both, it should be not high, or yeah, it should be the small one. Okay, the third difference will the valency of the two atom should be similar. And the number 4, what about the crystal structure also? The crystal structure of the both the two atom should be similar. So these are the four conditions, that is the Homer-O3 condition. So which is according to this question number? So which one is not the Homer-O3 condition? Just let me know which one is not the condition one. So which one is the not the correct one? Uh, is it the A, B, C or D? Which one is the not correct? In the first one, it is mentioned that the crystal structure of each element of the solid solution must be same. Yeah, this is the fourth one. So this is the correct one. Now in the B part, it is said that the size of the atom of each two elements should not differ by more than the 15 years. So this is also correct. Size of the atom of the two elements should not be greater than the 15%. Third one is the third one is the elements should form the compound with each other. No, it is not correct. Why? It is not mentioned there. The elements should form the compound with the each one. What about the fourth one? Fourth one is the elements should have the same valence. Yeah, both the elements have the same valence. So D is all the correct one. So only C is the incorrect statement. So C will be the right answer. Okay. Do you have any doubt till question number this means sixth one? Okay. If you have any doubt, please let me know. I mean, please feel free to ask any question. Okay. Okay, let's go to the question number 7 1. So now the in this question what question number 7 is the coordinate of the motif and the lattice type in a distorted nickel 3 aluminum 1. So what is the nickel 3 aluminum? So this is it is asked in bit in the distorted one. There is the one is the so you do you know about this structure of nickel 3 aluminum? Nickel 3 aluminum Nickel 3 aluminum is basically your 75% your nickel and the 25% your aluminum, and this is the distorted one, and this is the here in the they occupy the FCC lattice FCC1 with with the motif with motif at the rate of 0 0 at the 0 0 with I mean with this 75% nickel and the 25% aluminum one. For this is the condition for the distorted one. If I talk about the regular this the ordered one also ordered one. So another one type is the ordered one. Ordered one is the nickel 3 aluminum. Nickel 3 aluminum. So this is the simple cubic one having the motif at the because your this your I mean this nickel is at the FCC1 and aluminum is having at the corner of the this cube one. If this is one for this one for the this is your for the this one this will be the for the nickel one and aluminum will be at the corner of the cube one. So the motive for this would be the for the nickel is that is having that the phase center, so that will be the 1 by 2 0 1 by 2 1 by 2 1 0 1 by 2 1 by 2 and 1 by 2 1 by 2 0, and aluminum is having at the corner of the cube, so aluminum is having the motif at the 0 0 0 1. Okay, so this is the condition for the order one and distorted one because we have the normal it is FCC1 and we don't know because it is already distorted and each atom is having the 75% of nickel having the motif at 0 0 with the 75 because here this is the 3 times of the aluminum one, so 75% is the occupied with your nickel one and the rest 25% is occupied by the your aluminum one. So for this one the coordinate of the motif will be the 0 0 1 and the lattice will be the FCC 1. So B will be the right answer. Okay, let's move to the question number 8. So this question you have to tell me. So which of the following structure having the layered lattices? Diamond, magnesium, bismuth, and the phosphorus one.
So which of the one having the structure with the layer one? I mean, this is taught in your classroom lectures. So layer one, I mean, in the layered one, what kind of the bonding in that is existing in your layer lattice one? The in each layer, in the layer itself, bond is the atom are connected with the covalent bond, covalent bond, and between the two layer, or in the layer, between the layer, between two layer, if I say it, they are connected with the van der Waal forces. So that with the small forces, because the van der Waal forces are the weak forces, with the small forces they easily can be removed, or we can change their morphology. So which one is the correct option for the layer structure one? Diamond, magnesium, bismuth, and the phosphorus one. Which one is the correct one? Diamond is your basically carbon, magnesium, phosphorus, bismuth, and the phosphor. So I'm telling for this one, this you have to remember: diamond, bismuth, and the phosphorus. These are having the layered lattice web. Okay. If you see the periodic table, I can just let me. Okay, so this is the periodic. So the here is the carbon one, phosphorus, magnesium is not, and the bismuth one is. Where is the bismuth? It is. Here it is. So this group 15, mostly they are having the, because they are having the chances of the, in between them is the covalent bonding. So carbon also having the covalent bonding. So they are having the layers. Basically the atoms that are having the covalent bonding, mostly the covalent bonding, they are having the layer structure. So the diamond, manganese, and the phosphorus one having the layer structure one. Okay. Yeah, the bond between them is the covalent one. The carbon is surrounded with the 4 one. This is the carbon. So that's why it's existing in the layer structure, layer lattice one. There, your this carbon is shared with the 4 atom. That is the sp3 one, sp3 hybridized one. Are you getting my point? Pani, is it clear? Yeah, between the layer, if I talk about the carbon, they are the more or less the not the this one, the covalent one. If generally we talk about the this diamond one, so they are having the van der Waal forces, so that we can exploit them for the carbon, because we if you have seen for the graphite one also, that is also the other type of the carbon one, so that can be exploited. I mean, this layer structure is only existing for this weak forces. The covalent force is also weaker than your ionic bond also. So this is existing for the magnesium having the greater, I mean the ionization power. There the your this ionic bond existing there one. So in between there is only the covalent bond existing. So the layer structure will exist for these them. Okay, okay. Let's okay. Let's move to the next question. This is the question number 9. Okay, this same kind of the question, but in the different manner. It is our question number 9. That is the bond responsible for the lubricant nature of the graphite is A is the ionic bond, B is the metallic bond, C is the covalent bond, D is the van der Waals bond. So which one is the right one? D. The bond responsible for the van der Waals forces. The lubricant nature of the graphite is because of the because they are the van der Waals are the weakest one. They are ionic, metallic, and covalent are the strong bond compared to the your van der Waals forces one. So the lubricant nature will be uh, responsive which is due to your the van der Waals forces. So D is the right answer. So let's move to the next question, question number 10. So now what is the 4sp3 hybridized orbital adopt what kind of the symmetry one? So what kind of the symmetry that is existing for the 4sp3 hybridized orbital one? So there are the option in the linear. So one is the linear, second is your trigonal planar, third is the octahedral, and the fourth one is the tetrahedral one. So what kind of, okay, so let's discuss for the linear one. What kind of the hybrid orbital one? That is your sp1, sp, only the sp. So if the example will be your CO2, that is a sp hybrid orbital. And second one is the trigonal planar one. Trigonal planar having the sp2 hybrid orbitals. If I see the example for this one will be the BF3 one, BF3 or something in the term of no, not in the methane one. That is the tetrahedral one. If that is existing in the AX3 form, the example for this, the trigonal planar one will be the in the form of AX3, or they are having the hybrid orbital of sp2. Next one is the octahedral one. Octahedral one having the hybrid orbital of sp3 e2. That is basically S in the 6 coordinate one, SF6. The example for this, the octahedral one is the SF6, and next one is the tetrahedral. Tetrahedral is having the hybrid of sp31. SV31. Okay, so if here it is asked about the sp3 hybrid orbiter, so they will adopt the tetrahedral geometry one. If it is asked for the SP will go to the linear one. SP2, that is your trigonal planar one. SP3 tetrahedral, SP3 D2, or sometimes we write this one is the D2 sp3 that is having the octahedral. These are kind of the hybrid orbitals having the this corresponding this kind of the geometry one. Okay, so remember these one, linear having the sp1, the trigonal planar having the sp2, octahedral is having the sp3 d2, and this tetrahedral one with the sp3 one. Okay, so D is the D is the right answer. So let's move to the question number 11. Now it is a in which of the following, in which one of the following is the current correct bond angle between the atom adopting a trigonal planar geometry. Now you have to tell me about the what kind they in the last question we have discussed about the hybrid orbiter. So what kind of the hybrid orbiter existing for the different geometry, for the linear SP, for the trigonal planar that is SP2, tetrahedral one be the SP3 and the octahedral be SP3D2. So now you have to tell me the what is the angle, correct bond angle between the atom that is adopting these kind of the geometry one. So if you see from here, that is the see from here linear atom, linear that is whatever the linear, they having the 180-degree bond angle. The angle between this is the 180-degree bond angle. In the this is the trigonal planar because they are in the same plane. So these angle, this is the angle between two bonds, bond length, that is 180 degree. So trigonal is having the 120-degree bond angle. This is the tetrahedral. In tetrahedral, we know this kind of the structure we are having in the tetrahedral. They are having a 109.5-degree bond angle. Okay, in the this is the trigonal bipyramid. So they are having two different kind of uh, uh, angle. One is having the 90-degree, that is for the if I'm considering the this angle, and the 120-degree between these two. This is bipyramid. This is because of the two pyramid they are considered here, and they are the trigonal one also. For the octahedral, because octahedral 4 is in the same plane, one is upward and the same. So this angle, this is one out of the plane, that is upward one, and one is the below the plane. So angle between them is the 90-degree. So for the linear is having the 180-degree, trigonal is having your 120-degree, and the your tetragonal is having the 190 109.5 degree, and the octahedral is having the 90-degree. And similarly, for all of them, your hybrid orbital will be, remember this point, I mean, hybrid orbital having the sp, for trigonal is your sp2, tetragonal is the sp3, octahedral it will be the sp3 d21. Okay, so now in the discussion, it is asked about the trigonal linear geometry. So what will be the what will be the bond angle between the for the trigonal linear geometry? As we have already discussed, so this will be the 120-degree. So D will be the right answer. Okay. Do you have any doubt till this point? Question number 11. Do you have any doubt? No? Okay. Then let's move to the question number 12. Now, here it is asked the size of the interstitial atom that can fit into a tetrahedral void of a cubic closed packed structure formed by the host atom of the radius r. If any atom having the a host atom that is having the radius of r, so what will be the size of that interstitial atom that can fit to the tetrahedral void? If we have given an atom, the closely packed atom, let's say this is my closely packed structure, and it is having the atom whose radius is r. and I'm assuming the size of the interstitial atom that can fit into your tetrahedral voids is your RTR. Okay, so this is the R. So if this is the cubic closely packed structure, so that will be the FCC1. This one, this one, this one, here, this one here, and this and this. So this is the so basically you know your this tetrahedral void exists on the body diagonal of your of the cube one or the unit cell one. So it will be of this type. If I connect this atom and this atom and uh, uh, the this atom center of this one and this one, so it will be so the atom will occupy at the this position I mean, and this is at the body diagonal one. This is your 0 0 position and this is 1 by 4th of the body diagonal. So it will be the 1 by 4, 1 by 4, 1 by 4. Now we have to consider this length we know. Now I'm considering this length, that is we are having this atom. At the center of this atom is having the radius, or here is there is atom because they are closely packed. This is not the empty space here, so it is here is something atom here. That is, we have defined the radius of the R tetrahedral one, and this body diagonal of total length is the what is the body diagonal of a cube? That will be the root 3a, and it is existing at a 1 by 4th of the body diagonal because it is having the coordinate of 1 by 4, 1 by 4, 1 by 4. So this distance center to this atom center to this will be the root 3 a by 4 1. So now this R, that is the host atom radius, this one, plus this atom radius, that is plus the R tetrahedral one, will equals to 1 by 4th of your body diagonal. So it will be the root 3a by 4 1. Okay. Now because of, this is the FCC one, and we know the relation between the A and R for the FCC one. So in the this one, your body diagonal 4a is equals to, this is face diagonal will be the 2 atom radius. So this 4a will be the root 2a, or I can say okay. So now you have to put, because we have to find out in term of the R one, what is the size of the interstitial atom one. So in term of R, so I will put A will be the 4a by root 2, or either it will be the 2 root 2 into R. This is A is equals to 2 root 2 R. Now substitute in this one. That is your R plus R tetrahedral one equals to root 3 by 4. A will be the 2 root 2 R. And so this will cancel out, root 6 by 2 into R. This is R plus R tetrahedral. Now R tetrahedral will be the root 6 divided by 2R minus R. Just calculate this value, how much you are getting. So that will be the R tetrahedral, that the atom of this radius can fit to the tetragonal void that is existing with the, that this is the maximum size that an atom can occupy the interstitial site. I mean, occupy the tetrahedral void position. So how much you are getting for this one? Root 6 divided by 2 minus 1 into R. What's its value? Just calculate this value. How much you are getting for? Please let me know. Root 6 divided by 2 minus 1. So, okay, Pani, it is around 0.22 R. Okay, so then your R tetrahedral will be the uh, 0.22 R1. So this is the relation for the tetrahedral one. So according to this one will be the A will be the right answer. If somebody for this is the for the tetrahedral one. If it is asked for the octahedral, so how will you calculate for the octahedral? The same thing, octahedral one. Let's consider the structure. This is one atom are also at the face of the center as well. So these are at the same planes. Connect these then. This is for the below one, this one, this one, this one. For the octa, you have to find out the first the octahedral void and then you can fit there. If same question for the octahedral, because here it is asked for the tetrahedral void. Now I'm considering for the octahedral. So this is the one plane. So this one atom will be connected to this one. Again will connect it to all of them. The same one also connected with all of them. Now the whatever the atom that is here, that is fit here, that will be your the atom that can substitute in the octahedral void one. Now this distance is your A. Okay. Now and so what will be the distance? Because this is at the center of phase one. This is the at the I mean center of the face. This is also at the same. So it will be the same distance. This distance. Basically, this distance will be the same distance A. So if I'm considering the host atom radius R is R, and the atom that can fit into your the octahedral void that is having the radius R oct. Okay, so this is the R oct. So if I'm going, these are having the same distance. So it will be the R plus, because it is having the two, because these are on the same line, these are not the separately, there is no space between, we have already fit there and they are now closely packed. So this is the something like this one. This is the host atom, this is the R radius, this is having the, so this distance will be the twice of R oct, and this is also the R, so it will become 2, and this total distance is your A. So 2R plus 2R oct equals to A, this A, and this is A is your face diagonal one. So put the value of A here, that is A is the, we already calculated A is the 2 root 2 R, R 2R plus में 2R oct. Now you can cancel out the 2, so it will become R plus R oct is equals to root 2R. So your R oct will be the R oct will be the root 2 minus 1 into R. Root 2 is equals to 1.414 minus 1 into R. So it will be the 0.141 hour. So octahedral radius will be the 0.41, 0.414, and the tetrahedral having the radius zero point 0.2. So this is the radius for the octahedral. So R, so I'm writing for the R of will be the 0.414 R, and the R tetrahedral will be the 0.22. Then it will be the last number will be the 5 R. If somebody asks you that tetrahedral one, so you have to proceed here. First, find out the tetrahedral voids. Tetrahedral will be the four atom if you are that occupy the space at the in the I mean the tetrahedral position one, this one and the atom that can fit her. First you will find out and you will find out the what it will be the relation that void, that the distance with this atomic cell. So we know this is existing at the body diagonal and it is at the distance of the 1 by 4 of the, because it is having the motive the 1 by 4 1 by 4. So this distance we know this is the 1 by 4th of their body diagonal. Here the same thing is also happening for the this one. Here also there is this one, this tetrahedral void existing. So that's why we are in each body diagonal we have the two tetragonal and we have the four body diagonals. So total number of the eight tetragonal voids that are existing in the closely packed one. So then after you first you find out the this void, then the relation with the this one, and then you have to just use the formula and convert into the one term, because here it is asking the R term. So they convert this A, you know the relation between the A and R, then put this value and you can when you substitute this one you will get the R tetrahedral will be the 0.22 R. Same for the octahedral. If you go with this one, you know these are at the same distance, at the same line as the atomic A lattice parameter. So they are will be the total distance will be the A, because they are totally not closely packed. So it will be the 2R, because half R radius this one and the R radius this one, and this is the 2 of R oct. So total if you put at A, then you have to substitute the value of A here. We already know this value. Substitute here, and if you substitute this one, then you will get the R oct will be the 0.4141. Okay, so this is the size of the that is any atom. Or if somebody asks you the substitutional atom, what will the size of the substitutional atom? This is the interstitial, because that is having the space that is voids are basically the space that is existing between the different kind of the geometry one. So substitutional are basically having some kind of the lattice that is already presenting there. If somebody fit there, that is having the host atom. If the host atom having the radius of R, that depend on, because that's why we are the Hume-Rothery condition, that the size is much no, the size difference should not be the both the elements should not be the less more than the 15%. It should be the less than the 15%. So we have the more or less same of the size of the this the impurity atom also as the host atom. Okay, so this is for the question number 12. Now move to the question number 13. So now you have to tell me what is the uh, diamond crystal structure. Diamond crystal structure. What will be the diamond? We have already discussed about the zinc plate. What is the structure of the zinc plate? It is more or less same of the zinc plate one. So you have to tell me. So what will be the crystal structure for the diamond one? So what will be the crystal structure for the diamond crystal structure one? So if you see from here, this is the diamond structure, uh, because there is a two, if you say, each carbon atom at the one is at the corner, cubic one, same as the cubic one, this cubic one, and the another two motif that is existing at the 0, 0, 1, 0, 0, and that is another one is the 1 by 4 distance as this one. If we will this is the projection, uh, just look at this one only now, for as of now. So if you say there is a simple cubic one, because we are existing, and here the another motifs that are also existing here, because this is the tetragonal that is having, that is one is at the 0, 0, and another is the 1 by 4 and the 1 by 4. This thing is, as the professor also discussed in the classroom, thing is that this will be visualized when you project. Okay, sorry. This will be clear when we put this all kind of the atom into the projection one. When we take the projection of this lattice into the bottom part one. If you take this one, so you can find out, yeah, this atom having that the same position. The corner one is also having 0, 1, because 0, 1, it is 0, 1, it is written because one is at the zero plane and one at the a distance, the upper one, 0, 1, 0, 1, that's why 0, 1. Now these kind of the atom having, because this is at the center of this one, because this is the face center also, face center one also, no, this one is the face center one, face cubic says face center one. So this here is one atom here, here also for this one is and two atom are that are having the this so half at the face center. So this is 1 by 2, 1 by 2, 1 by 2, 1 by 2. Now this is atom, this m atom, if you project here, so this is at the distance of 3 by 4. And for the t atom, this one, this will at the, because here it is 0 and same atom will be at the upper and same, because this is the phase projection of same atom, this one and this one, that's why 0, 1. If you consider this k atom, this is not the phase diagonal one. If you project here, so that will at the distance of 1 by 4. Similarly for the your n will go to the 3 by 4, and your l, because these are only the four one. This is l, l, k, k, l, m, n. These are the different. Other will be the other are the face centered one and the cubic one with the same one. So this way they are having the FCC lattice, because of that the same this is at the face center one, and two at the lattice, that is one is having the, if I put this at because this is, if I put this lattice, this is at the 0, 0, and if I put the another lattice, that is a distance of the 1 by 4, 1 by 4, and 1 by 4. So same kind of lattice we can find out if I draw. So this will be at the same distance. Here this will become, so we can say this lattice, for this lattice, this will, if I draw for this one, this one is the FCC. FCC is the your FCC is the lattice, and your motif existing, because for this FCC lattice, that is the motif existing at the 0, 0, and the motive existing for this one, for because here the center we are considering at the 1 by 4, 1 by 4, 1 by 4, 1. Okay, for this, for FCC, this one, this is your center one, the face center one. For this one again, for this one it will become the this center one. For this one, if this is the face one, this will become the center one. Okay, so your diamond cubic structure will be the FCC one, having the motif is having one at the 0, 0, 0, 0, and the another one is will be there the 1 by 4, 1 by 4, and the 1 by 4. Okay, so if I see the I mean option for this one, so from this one we have the FCC one for the in the B and D. So but D is having at the distance of 1 by 2, 1 by 2, no. It is having at the motif at having the 0 0 1 by 4 1 by 4. So your B is the right answer for the body diagram. Okay, is it clear? Is it clear? Yes, okay. Okay, then let's move to the next question. Okay, in the next question, okay, the close packed plane in the direction in the HCP lattice are. Okay, so this you have to tell me. In the last class, we also discussed the same thing. What is the close plate direction for the FCC, for the cubic one, and for the BCC one, for the HCP one? What are the close plate direction and the planes one? For there, we have to discuss the same question. There, it is here. I mean, it is repeated. So, what will be the close peg direction and the plane for the HCP one? Tell me what will be the close plane direction and the what will be the close plane and the corresponding direction one. Close plane, which is closely pegged. I mean the pecking fraction of closely pegged. That what which plane that is closely pegged and what is the direction that is closely pegged in case of the FCC. In the HCP here it is asked. In the last class we have discussed for the BCC one. Let me remind you. For the BCC one, we have the close direction in the that is 1 1 1. For the FCC one, we have the close peg plane that is the 1 1 1 and the here direction because that is the face center. So this is the direction is 1 1 0. For the HCP, we have considered the close sorry close peg plane will be the family of plane that is the 0 0 1 and direction will be the 0 1 0 or we can say write it as the 1 0 minus 1 0. So these are the closely pegged direction and the plane for the different kind of the structure one. Whether here it is asked, so the plane will be the 0 0 1 and direction will be the 0 1 0 or it will the shape different form is the plane because this is the set of the direction, so it will be the same as the 1 1 0 same. Or if I write in the another form, so this will be the 1 1 minus 2 0 as well also, or 1 1 0 1 and plane will be the 0 0 1. Okay, so remember these the close peg direction and the plane for the each of the crystal, each of the symmetry one. Okay, so 0 0 plane here or 1 1 0, this is the direction and the plane for the HCP lattice one is the right answer. The same thing in the D also. So A and D are the right one. Okay. So move to the next question. That is the question number 15. So if the lattice parameter is the CSCL is A, that is given A is the 3.995 angstrom. So what will be the bond angle between the bonding species is? Now you have to find out the angle between them. So how will you calculate the this is the bond length. So you have to calculate the bond length. Bond length you can calculate this is atom having. So what is the bond length for this one? So how will you calculate for the bond length? I mean, so firstly you have to you need to ask what is the structure for the CSCL. CSCL is existing at the BCC as a BCC existing in the BCC lattice one. Okay, lattice structure. So here this is your Cesium is this atom, center atom, that is at the body diagonal, and the chlorine atom that is at the corner of the cube one. Okay. Now you have this A is given to you, and you have to find out the bond length. The bond length between the two atoms. What is the bond length between the two atoms? So simply this is this distance. If I am say this is R, you have to calculate. You know about the body diagonal. This is the body diagonal one. If you know the body diagonal and you know the A and you know the relation between the A and R, this A and R relation, and you know what is the body diagonal, R is the radius. So then you can calculate the width will be the bond length of between CS and the Cl. So what will be the bond length? So as you know, there's a body diagonal of a cube is the root 3a. Okay. Now this body length, so bond length will be the half of this one. So bond length will be the half of this body length. Bond length. So this no, this atom. So this is having the radius r, and this is also having the radius r. So I'm considering the same of size. So what will the bond length? Now what is the so what will be the bond length between the if the CaCSL having the 3.99 lattice parameter. So what will be the bond length? It is having the half of this value. So put the half of this value, 3.995. So this is the bond length of your between the species your CS and Cl. So how much you are getting for this one? I mean the root 3 by 2 into 3.995. If you calculate this one, root 3 into 3.995 divided by, so this is around the 1.7 divided by 2 multiply 3.995. This will come out, this will come less than this value, so it will come around the 3 point something value. Are you getting the same value? How much you are getting for this one? Because bone length will be the half of the body length, body diagonal one. So 3.46. So yeah, so your A will be the right answer because bone length will be the half of the body diagonal. So CSES, if somebody asks you about the, because this is having the BCC lattice, so you have to remember, I mean, at least the sum of the structure which are in the which form they are existing. And this NaCl, CaCl, carbon, diamond, and these one mostly. Because sometimes it is not mentioned in which kind of the lattice crystal structure they are existing. So you have to remember this one, and then so that you can easily put the formula and can calculate their value. Okay, so this is all about the assignment number 4. Let's me discuss from the again from the first one, just in a brief one. Okay, then then we will come to your question one. So in the first question they have asked about the what which type of the interstitial site will your iron and the titanium occupy in the FeTiO3. Basically FeTiO3 is existing in the form of AbO3. So if you look at this one, so your Fe and the titanium is surrounded by the six oxygen atom in the both the lattice one. Here you can't see, so we have put another figure. Here you can see this is the something tilted one. So here you can see this one. This is the golden one is your Fe1, titanium is the blue one, and orange is your the oxygen one. So this is connected to the six one, or this is surrounded by the six in the octahedral one. So your Fe2 positive, and the same for the tetrahedral because it is also forming these six oxygen also forming at the octahedral. From here you also can see from the this one. So these Fe2 positive and the TiO4 positive both are existing in the octahedral position one. Okay, so now so for this one, so you have to know about in ABO3 structure where my A and B are, I mean, occupy the position. So for you, you have to know about the ABO3 structure for this one. Okay. In the second question, we have the zinc plate crystal structure, and you have to find out in which crystal structure they are existing. So we have already taken this sulfide the FCC one, and the zinc will occupy half of the tetrahedral one. So the sequence will be the your FCC one. Okay, similarly here the I mean these are having similar like to your diamond on the silicon carbide one also, because they are we have already discussed in the last question, I mean last or I mean in the last one. Yes, they are also having the FCC one, but the with the motive of the 0 0 for the diamond one 0 0 1/4 and the 1/4 and the 1/4. Same thing. For the third question, we have to find out the coordination number for the cation, that is having for the octahedral and the tetrahedral. We know the for the octahedral that is surrounded by the six atom, because and for the tetrahedral it is surrounded by the four atoms. So this will be the coordination number for the tetrahedral will be the four, octahedral it will be the six one. In question number 4, how many tetrahedral voids per atom is possible in the HCP? So in the FCC and FCC, they have the same number of the voids. So the in the if the number of that in the tetrahedral that are having the 8 per unit cell, and in FCC we have the 4 atom per unit cell. So this will be the 2 per atom. Remember, in the case of the FCC, it will be easier to think. So and say it the same will be happen for the HCP one. So number of the tetrahedral void in the FCC, that will be the 8 per unit cell, or that will be the 2 per atom. In the octahedral will be the 4 per unit cell or the 1 per unit atom. So same thing will happen for the HCP one. Number of the tetrahedral will be the per atom will be the 2, and the octahedral will be per atom will be the 1. Okay. In the next question, they have asked about the which of the statement is incorrect. So we have discussed about the substitutional. Substitutional is basically where you the impurity of the solute atom that is, I mean, sit at the lattice of the solvent atom or the host atom. Interstitial that is having the where the impurity or the solute atom occupy the interspaces between your solvent atom, that the space that is between your the solvent atom. Intermediate compound, that is in between the compound form, the compound form between the two atoms. If any reaction is going on from A to B, so whatever the form or the phase of the material compound that is formed between them, that will be the intermediate compound. And the next one is the intermetallic. Intermetallic are the well-defined your crystal structure, and also having the well-defined stoichiometric coefficient, because in the this example N9 3 aluminium, we also see in the ordered one and the distorted one. In this one distorted, in the distorted one they having the 75, on ordered one they have the specific one where they are sitting on when they are not sitting. So the this is the your intermetallic compound one. Okay, in question number 6, what are the condition for the Homey-Rothery condition? There are the 4 conditions where the size should be the less than the 15%. Your electronegativity should not be, the electronegativity difference between the two atoms should not be large. Third is the valency of the two atoms should be of the similar. They are having the same kind of valency. And the fourth one is the crystal structure of the two atoms should be the similar one. So this C part, the elements should form the compound with each other. It is not true. So this is the incorrect statement for the Humero 3 condition one. In the seventh question, they have asked about the this or disordered A nickel 3 aluminium. For the disorder, what is the motif and the lattice one? This is the same one, the motif at 0, 0 with the 75% nickel, and the FC they are existing at the FCC one, and with the 75% nickel and the 25% of the aluminium one. Or if I talk about the order one, they are order one. In it is shown that the aluminum will occupy the 0, 0 motif, and this in the this nickel will occupy at the face center of the cube one. Uh, in the question number 8, what is the layer structure? Layer lattice, diamond, magnesium, bismuth, and phosphor. So diamond, bismuth, and the phosphor. Generally, here the covalent bonding weak forces lead to your layer structure. Metallic ionic will not go to the, and metallic also, or metallic compound will mostly having the ionic, or more or less they are some of them are having the mixed behavior with the ionic with the some percentage of the covalent. Generally the layer that is having the layer that is having the covalent or the weak forces one, the covalent, and this weak van der Waals forces one. In question number 9, this is the bond responsible for the lubricant nature of, because the weak forces that can give you the lubricant nature, so the van der Waals forces will be the responsible for the. In next question, so the 4sp3 hybrid orbital, what kind of adopt the what kind of symmetry? So generally sp will lead to the linear one, sp2 the trigonal planar one, octahedral will give you to sp3d2, and the tetrahedral will give you the sp3 hybrid orbital one. And the next question they have asked about the what is the bond angle between them. So for the linear it is the 180 degree, trigonal planar it will be the 120 degree, tetrahedral is the 109.5, octahedral it is the 90 degree, and the trigonal bipyramidal it is having the 120 and the 90 degree. In question number 12, we have find out the size of the interstitial atom that can fit into the tetragonal void with the radius r. So this we have calculate with this one. First consider the void, tetragonal void, and then consider any atom that are fitting there. So from there and put the relation, the known relation with the atomic this the lattice one, and compare with the, you know, the relation between the E and R. Just put this value, and if you when you substitute, then you will get the relation between the size of the atom that is fitting into the tetrahedral void and the host atom also. I mean the 22, this is the 22% of the host atom of that atom. I mean of that size, an atom can fit to the octahedral one. This is the tetrahedral one. For the octahedral, the 41% of the size of the host atom can fit to the octahedral side one. Same thing can happen for the octahedral one. Okay. In question number 13, it is asked about what is the motif and the lattice for the diamond one. So you have to remember the important standard crystal structure and how their lattice and the motif. I mean, what is the motive, or the either you have just remember where your atom are existing or occupy the space, so that you can find out the lattice and the motif of the crystal structure. Remember for the standard some crystal one. In the 14 one, it is also the ask about the close peg direction and the plane in for the HCP. We have discussed this thing in the last class. Also for the BCC, we have the direction. This is 1 1 plane, and the this FCC one. This is also the 1 1 plane. For the HCP one, it is the 0 0 1 plane. In the last question, we have discussed about the what will be the bond length, and bond length will be the, we know that the CHM chloride existing in your BCC lattice, so your bond length will be the half of the body length. So just substitute these value. A is given this, when you put this value, and you will get the what will be the bond length of the species one. Okay, so this is all about the assignment number 4. So if someone has any query, just let me know. Does anyone have any doubt in assignment number 4? Nothing in this session. Okay. So, Pani, your doubt is in assignment number 2. Let me put that figure here. Um, just a second. We'll come to that point one. So, I think the set 2 is clear to you. So, we have to discuss only the set 1. Set 2 you can see from here. Set 1, if you now we for this question we have to consider, we have to set the such vectors that can give you the BCC in the BCC lattice that can give you the primitive one. And as I already told you, the primitive one that is having the one atom per unit cell, but in the BCC we are having the two atoms per unit cell. Now we have to anyhow we have to convert this your body diagonal atom into the corner one, same one. So I'm considering that this is the one lattice. Okay, okay, just a second. It will be harder to visualize. Let me go with the dotted line. This is the unit cell, and your atom are presenting are here at the corner and at the body center. So let me do at the corner first. These are the corner one, and I'm considering for this unit cell let's say it is here the body diagram, and for this one it is here, and for the next two unit cell body center, for their body diagonal is somewhere here. Is it clear up to this point, Amin? Are you with me? Okay. Now we have considered the, let's say this is my in the, this is my x direction. We have considered in the x, y, and in the, this is at the body diagonal, half of the body diagonal. This is my x, y, and the perpendicular to this one in the this is my y, x, y, and this is the my z one. Okay, this is the my parameter. So I am considering this. Oh, sorry. Okay, so this is one my letter. One. Another one is this one, and another one that I have considered this one. This is the straight line. Now consider this one also as one. Okay, let me consider this atom it little bit here. I mean, so this will be the, again for the this body diagonal. Well, this one. I'm connecting this one. Okay, so can you see this is the one of the face of the cube? If I'm considering this well, this one is the one of the face of the cube. This one. Yes. Okay. Now I will consider the another atom. It is not necessary that it now the primitive unit cell should be from the this single unit cell. So I'm connecting this one to the this atom. I mean next one. This one to the next body center, and this atom to the next body center. Okay. So this is another one plane, and this is one plane. These both are the parallel plane. This is not in the drawing, but both are the parallel one. Okay, now if you connect them, so another will be the, this will be the third bottom one. So this will be the primitive one. Okay, got you? Okay, okay. Now is it clear, na? I mean, you have to connect your body diagonal. So this one is your one of set of letter, and another is a set of unit vector. This one, and this third one is the body diagonal one. Same you have to consider for this one, and there you will get your body diagonal will come into the this is the, into the will become the corner of the cube. Okay, okay, okay. Now hope so. This is clear to you. The second one is here. It is also here. It is shown you in the diagram one already. The B part set two is clear or not? I mean, yes. Okay, okay, okay. Okay. Does anyone have any other doubt in assignment number 4, or in any other doubt in the other assignment as well? If someone had doubt, then you can raise your hand and cover and can ask the question also. You can unmute yourself and okay. If not, then you can leave the meeting. And sorry for the inconvenience today. I am not feeling well, so this there is disturbance throughout the lecture one. So sorry for this inconvenience. You have tolerated me for this one. Yeah, I will take care. You too also take care. Okay, then I mean, if somebody don't have any doubt, you can. I mean, leave the meeting or we can cancel this meeting. Okay, thank you. Kalpana, do you have any doubt? Kalpana, do you have any doubt? I don't, there's no response from you, so I'm just waiting for you just to. Okay, Kalpana, if you don't have any doubt, you can leave the meeting. Okay, I'm just leaving this meeting. If you have any doubt, you can ask me, or either you can mail me, or you can ask the discussion form there. We will reply you there, or you can mail us also as well. Okay, thank you, everyone.